Neutron stars are the strangest objects in the universe, heavier than the Sun yet no bigger than a city. But how can something so small bend space-time and even light itself? This is the ultimate journey into nature's most extreme stars. If you enjoy it, please like, subscribe and share, and tell us in the comments what blows your mind most about neutron stars. Thank you for watching. Now let's begin. A star begins its life as a vast cloud of hydrogen gas. Over long stretches of time, gravity draws the gas inward until pressure and temperature at the center rise high enough for nuclear fusion to ignite. In most stars, this process sustains a steady balance, with the energy from fusion pushing outward against the pull of gravity. But in stars with much greater mass than the Sun, the sequence of fusion stages continues further. First, hydrogen fuses to helium, then helium to carbon, and then progressively heavier nuclei build up in the core. Each stage occurs faster than the last as the core grows hotter and denser. Eventually, elements such as oxygen, silicon, and sulfur form layers within the star like shells nested one inside another. At the very center, iron is produced. Unlike lighter nuclei, iron does not release energy when fused. Instead, it consumes energy, and so fusion cannot proceed further in the same way. When iron accumulates in the core, the star approaches a final limit. The star's gravity presses inward relentlessly. For millions of years, the outward flow of fusion energy resists that weight. But once the iron core grows large enough, the balance is lost. In a matter of seconds, gravity overwhelms the central region. The core contracts and the density rises to levels greater than atomic nuclei on Earth. Under this intense pressure, protons and electrons are squeezed together into neutrons, releasing a flood of neutrinos that carry away energy. The collapse happens so rapidly that the outer layers of the star cannot respond immediately. They fall inward, striking the dense central core and rebounding outward in a tremendous shock. This shock, aided by neutrinos streaming from the core, drives away the outer layers of the star in an event known as a supernova. What remains in the center after the collapse is no longer like any ordinary star. It is incredibly compact, containing more mass than the Sun, but squeezed into a sphere only about 20 kilometers across. This is the neutron star. Its birth marks a transformation of matter into a form that does not exist naturally on Earth. The density reaches values close to nuclear density, meaning that a spoonful of neutron star material would weigh billions of tons. Gravity at the surface is so strong that light struggles to escape. Time itself runs slightly slower there compared with distant space, an effect predicted by general relativity and confirmed by measurements of signals from neutron stars. The creation of such an object is not an exotic rarity. In the galaxy, core collapse supernovae occur every century or two, though most are hidden from direct view by gas and dust. Each event leaves behind either a black hole if the mass is great enough, or a neutron star if the collapsing core is in the right range. The distinction depends on how much matter falls inward and how the core stabilizes. If the mass is below about 2.5 times that of the Sun, the neutrons in the dense core provide enough pressure to resist complete collapse. Above that threshold, no known force halts gravity, and a black hole forms. Neutron stars are remarkable because they represent the threshold where nuclear physics and astrophysics converge. The pressure inside them is provided not by thermal energy or radiation, but by the quantum mechanical properties of neutrons themselves. The same rules that keep electrons from occupying identical states in atoms also apply to neutrons in dense matter, and this degeneracy pressure halts the collapse. Without these quantum rules, matter, at such density, could not resist further compression. This is why neutron stars can remain stable for billions of years after their violent birth. Observational evidence of neutron star formation comes from both the supernova explosions themselves and the compact remnants left behind. In some supernova remnants, astronomers detect rapidly rotating pulsars at the center. These pulsars send out beams of radio or X-ray light that sweep across Earth like a lighthouse as the star spins. Their presence confirms that the collapse of the star did not end in a black hole, but in a neutron star with a strong magnetic field. Other supernova remnants contain faint X-ray sources without regular pulses, showing the variety of outcomes that follow the same general collapse process. The path from a massive star to a neutron star is a stepwise chain of physical processes that astrophysicists trace with both theory and observation. Nuclear reactions build up heavier elements until iron halts further fusion. Gravity then drives a collapse in less than a second. Neutrinos stream outward, carrying away much of the energy, while a shock front reverses the infall of the outer layers. The expelled material seeds the galaxy with heavy elements, while the compact neutron star remains behind as a dense relic. The newly formed star spins rapidly since angular momentum is conserved as the core contracts. A star that rotated only a few times per month can become a neutron star rotating many times per second. Magnetic fields compressed during the collapse intensify to levels trillions of times stronger than those near Earth. From the moment of its birth, the neutron star is an extreme environment. Astronomers study these processes not just through light, but also through particles and waves. Neutrinos from a nearby supernova were detected on Earth in the year 1987, providing direct evidence of the core collapse process. More recently, gravitational wave detectors have begun to measure ripples in space-time from massive stellar events, confirming theoretical predictions. Each detection offers insight into how neutron stars form and evolve. Still, many details remain uncertain. The exact way in which the shock wave overcomes the infall of matter, for example, is a subject of ongoing research. Supercomputers simulate these events incorporating nuclear physics, fluid dynamics, and neutrino transport, yet the full mechanism is complex. What is clear is that from the death of a massive star, one of the most compact and enduring objects in the universe arises. In this way, neutron stars begin as the natural consequence of stellar evolution. They are not anomalies, but expected outcomes for stars above a certain mass. Their existence ties together nuclear physics, relativity, and observational astronomy. Each newly discovered neutron star is a reminder that the life cycles of stars produce both destruction and creation-destruction in the explosive loss of outer layers and creation in the emergence of a stable, dense remnant that persists for cosmic timescales. From the calm light of hydrogen fusion to the sudden collapse of the core, the path is continuous, driven step by step by the same laws of physics. The neutron star is simply where these laws lead, when matter is pushed to the limit. When the collapse of a massive star reaches its final stage, the moment is swift and violent on cosmic scales. In less than 1 second, the iron core contracts under the force of gravity, falling inward at a fraction of the speed of light. During this collapse, electrons are forced into protons, creating neutrons and releasing a flood of neutrinos. These nearly massless particles escape through the dense matter, carrying away an enormous amount of energy. The rapid contraction halts when nuclear densities are reached and the core stiffens abruptly. This sudden stop creates a rebound like a compressed spring releasing. The outer layers, which are still falling inward, collide with the stiffened core and form a shock wave. For a brief time, the shock struggles to push outward, losing energy as it moves through the infalling material. Without an additional source of energy, the shock would stall, and the star would continue collapsing into a black hole. The neutrinos streaming from the dense core provide that energy. Although neutrinos interact only weakly with matter, the enormous number produced during collapse means that some are absorbed by the surrounding material. This heating, combined with turbulent motions in the stellar interior, revives the shock and drives it outward. The result is the explosion known as a core collapse supernova. In a matter of hours, the shock front tears through the star, ejecting its outer layers into space. The material spreads at speeds of thousands of kilometers per second, enriching the surrounding interstellar medium with newly formed heavy elements. What was once the core of the star is now left behind as a dense neutron star no larger than a city yet containing more mass than the Sun. The conditions during this birth are extreme beyond everyday comprehension. The density of the core reaches about the same as the nucleus of an atom. Temperatures climb to hundreds of billions of degrees during the brief collapse. Gravity at the surface of the new neutron star is so strong that if a person could somehow stand there, they would weigh hundreds of billions of times more than on Earth. Of course, no solid body can survive such conditions. Even light is strongly bent by the star's gravity curving around it and allowing distant observers to see more of the surface than would otherwise be possible. Time dilation occurs as well. For each second experienced on the surface of a neutron star, a distant observer would measure slightly more than a second. Immediately after formation, the neutron star is hot, glowing with X-rays as it cools. Over thousands of years, the surface temperature drops, yet the interior remains warm for millions of years due to slow release of heat and possible exotic particle processes. The magnetic field compressed during collapse can reach values 1 trillion times stronger than the field near Earth. The rapid rotation inherited from the original star is magnified as the radius shrinks. By conservation of angular momentum, a core that rotated once every few days may become a neutron star spinning several times per second, or even hundreds of times per second in special cases. The newborn neutron star is therefore both hot and fast, a compact engine radiating energy into space. The environment around the forming neutron star also undergoes change. The expelled layers of the supernova crash into surrounding gas, creating a glowing shell known as a supernova remnant. This expanding cloud emits visible light radio waves and X-rays as shock waves accelerate particles within it. In the center, the neutron star itself may reveal its presence through pulses of radio light, or through steady emission of X-rays from its hot surface. Some supernova remnants contain a bright pulsar wind nebula, where the rotation of the neutron star powers streams of charged particles that light up the surrounding gas. These observational signatures allow astronomers to connect the remnants seen in the sky with the theoretical models of collapse and neutron star birth. Despite decades of research, the details of how the shockwave becomes successful in ejecting the outer layers remain a subject of investigation. Three-dimensional computer simulations that include neutrino transport magnetic fields and fluid turbulence are among the most complex models in astrophysics. These efforts show that the collapse is not perfectly symmetric. Instabilities and swirling motions within the star influence the outcome, sometimes aiding the shock and sometimes hindering it. Observational data from supernovae in other galaxies provide constraints, but because such events are rare and distant, detailed information is limited. The detection of neutrinos from the supernova in 1987 gave a brief but vital glimpse of the core collapse process. Future nearby events would provide far more data, as neutrino detectors are now much larger and more sensitive. Another line of evidence comes from gravitational waves. The violent motions of matter in the collapsing star generate ripples in space-time, though at levels still below current detection limits for most events. If a supernova occurred within our galaxy, it might be within reach of the advanced detectors now in operation. A confirmed detection would offer a new way to probe the birth of neutron stars, complementing the information from neutrinos and electromagnetic signals. Together, these messengers form the growing field of multi-messenger astronomy, in which different forms of data combine to reveal complex astrophysical phenomena. The first moments of a neutron star's life are therefore both violent and fleeting, but they set the stage for everything that follows. The density reached in the core determines whether the star stabilizes as a neutron star or collapses further into a black hole. The initial spin rate and magnetic field strength shape how the star appears to observers, whether as a pulsar, a magnetar, or a quieter X-ray source. The energy carried away by neutrinos determines how much of the outer star is expelled and how much falls back. Each of these outcomes is rooted in the same brief moment of collapse when matter is compressed to its most extreme state. Astronomers approach these processes not as distant curiosities but as laboratories of physics under conditions unreachable on Earth. The matter inside a neutron star behaves according to nuclear forces that are still not fully understood. The neutrinos streaming from the core provide clues about interactions of particles at high densities, the gravitational waves that may accompany the collapse test general relativity in regimes of extreme curvature. Every new observation of a supernova or a young neutron star is therefore a direct test of fundamental physics. This is why the moment of collapse holds such importance in astrophysics. It is the bridge between the predictable sequence of stellar evolution and the exotic domain of ultra-dense matter. To understand what it means for a neutron star to exist, one must consider the scale of its density. On Earth, the density of common materials such as water or rock can be measured in grams per cubic centimetre. Even the dense core of our planet, composed mostly of iron, reaches only about 13 grams per cubic centimetre. By contrast, the average density of a neutron star is about 100 trillion times greater. That means that a cubic centimetre of neutron star matter would weigh hundreds of millions of tons. The numbers themselves are staggering, but the significance lies in what they tell us about the nature of matter when pushed to the limits of compression. In ordinary matter, atoms consist of nuclei surrounded by electrons. Most of the volume of an atom is empty space defined by the electron cloud. When the core of a massive star collapses, the immense pressure squeezes protons and electrons together, eliminating that empty space and forming neutrons. This process removes the familiar atomic structure, leaving matter that is essentially one enormous nucleus. At this density, the distinction between individual atoms vanishes. What remains is nuclear matter extending across the whole star. The gravity at the surface of such a dense body is equally extreme. A pebble dropped from a height of 1 meter above a neutron star would strike the surface in less than a millionth of a second, reaching a speed of nearly 100,000 kilometers per second. Escaping from the surface requires speeds approaching half the speed of light. This immense gravity warps space around the star. Observers far away see light from the star's surface bent around it, so that more than half of the sphere is visible at once. The gravitational redshift also stretches the wavelength of light, so photons leaving the star are shifted toward lower energy. These effects are not theoretical abstractions. They have been measured in X-ray spectra of neutron stars, confirming the predictions of general relativity. Rotation adds another layer to the description. When the core of the original star collapses, its radius shrinks from thousands of kilometers to about 20. Conservation of angular momentum dictates that the spin speeds up in the same way that a figure skater spins faster when drawing in their arms. The result is a newborn neutron star rotating several times per second, or in some cases hundreds of times per second. Such rapid rotation means the equator of the star moves at a significant fraction of the speed of light. The stability of this spin over long timescales is one of the most precise natural clocks known. Pulsars, which are rotating neutron stars with beams of radiation, can be timed with accuracies rivaling atomic clocks. The density and gravity of neutron stars also influence how we think about pressure. In normal stars, thermal pressure from hot gas balances gravity. In neutron stars, the primary support is not thermal, but quantum mechanical. Neutrons are fermions, meaning they obey the exclusion principle, which states that no two identical particles can occupy the same state. At high densities, this principle creates degeneracy pressure, a form of resistance to further compression. It is this pressure combined with nuclear forces between neutrons that halts the collapse and stabilizes the neutron star. Without these quantum rules, gravity would continue unchecked until a black hole formed. The concept of density at this scale is difficult to visualize, but comparisons help clarify. If one could take a sugar cube-sized piece of neutron star matter, it would outweigh Mount Everest. If the Earth were compressed to neutron star density, it would shrink to a sphere about 200 meters across, smaller than a large city park. These comparisons do not fully capture the physics, but they provide a sense of the profound change that occurs when matter is compressed beyond atomic structure. Evidence for such density comes from several types of observation. The timing of pulsars shows how small and massive they must be, since no larger object could rotate so quickly without breaking apart. The X-ray emissions from neutron stars in binaries reveal their compactness through eclipses and surface hotspots. Gravitational wave signals from merging neutron stars give information about how matter deforms under extreme compression, constraining the relationship between mass and radius. Each of these observations reinforces the conclusion that neutron stars represent a state of matter at nuclear density inaccessible in any laboratory on Earth. Density also determines the maximum possible mass of a neutron star. If too much matter is added, the degeneracy pressure of neutrons can no longer resist gravity, and collapse to a black hole occurs. The exact maximum mass is uncertain, but observations of the heaviest pulsars suggest it is at least about 2 times the mass of the Sun. Theoretical models propose an upper limit of around 2.5 solar masses, though the details depend on the unknown physics of dense matter. This boundary is a crucial area of research as it directly connects astronomical observations to nuclear theory. Another consequence of extreme density is the energy released during accretion. If material from a companion star falls onto the surface of a neutron star, the gravitational energy released is enormous. A single gram of matter falling onto the surface releases as much energy as a large power plant produces in years. This explains why accreting neutron stars are among the brightest X-ray sources in the sky. The compactness of the star ensures that even small amounts of infalling matter generate intense radiation. Cooling is another aspect influenced by density. Neutron stars cool by emitting neutrinos from their dense interiors, especially in the first 100,000 years of their life. The rate of this cooling depends on the composition and density of the core. If exotic states of matter exist inside, such as deconfined quarks, the cooling may proceed faster. Observations of surface temperatures in young neutron stars compared with theoretical cooling curves provide indirect evidence of these interior processes. In this way, density not only defines the structure of the star, but also affects its evolution over millions of years. The density of neutron stars, therefore, is not just a numerical fact, but the foundation of their existence. It explains why they are compact, why they can spin so rapidly, why they emit powerful radiation when accreting, and why they serve as unique laboratories for physics. It also defines the boundary between neutron stars and black holes, a frontier that astronomers continue to explore. In every sense, density is the essence of what makes a neutron star unlike any other object in the cosmos. The surface and crust of a neutron star are among the most unusual regions in astrophysics, because they provide the boundary between space and the dense nuclear matter below. Unlike the gaseous outer layers of normal stars, the exterior of a neutron star is solid. The outermost surface is thought to be only a few centimeters thick, composed of a dense layer of nuclei and electrons arranged in a crystalline lattice. This crust is held together by immense gravity, and its density already exceeds that of the densest materials on Earth by many orders of magnitude. From this thin surface downward, the structure changes gradually in a way that reflects the balance between nuclear forces and quantum effects. Just beneath the surface lies what is called the outer crust. Here, nuclei are packed tightly in a lattice, and electrons flow freely around them. The density increases with depth, and as it does, the nuclei become more neutron-rich. Under extreme pressure, neutrons can drip out of the nuclei and form a gas between them. This marks the transition to the inner crust, where a mixture of nuclei-free neutrons and electrons coexist. The nuclei in this region adopt unusual shapes due to the competition between nuclear attraction and electrostatic repulsion. Instead of remaining spherical, they may stretch into rod sheets or more complex configurations. These exotic arrangements are collectively referred to as nuclear pasta, named not for culinary similarity, but to describe the variety of structures. Although the terminology is light-hearted, the physics is serious. The properties of nuclear pasta affect how heat and magnetic fields move through the crust. Deeper still, the crust transitions into the outer core where nuclei dissolve completely, and matter becomes a dense fluid of mostly neutrons, with a small fraction of protons and electrons. The density here is about that of an atomic nucleus, and the particles move in ways governed by nuclear interactions rather than chemical bonds. The crust above this fluid core is only about 1 to 2 kilometers thick, yet it plays an outsized role in the behavior of the star. The solid crust is rigid and can store stress. When that stress is suddenly released, the result can be a starquake producing observable changes in rotation or bursts of radiation. These events provide evidence that the crust is not merely a passive shell, but an active region influencing the overall dynamics of the star. The crust also affects how the star cools. Heat from the core must pass through the crust to reach the surface and radiate into space. The composition and structure of the crust determine how quickly heat can flow. For example, impurities in the nuclear lattice can scatter electrons, reducing thermal conductivity and slowing the escape of heat. Observations of neutron stars cooling after episodes of accretion provide data that help scientists test these models. By comparing theoretical predictions with X-ray measurements of surface temperatures, researchers can infer details about the crust structure and composition. The crust is also where magnetic fields are anchored. Neutron stars possess magnetic fields far stronger than anything achievable on Earth. These fields thread through the crust and influence how the star interacts with its surroundings. Stress on the crust from shifting magnetic fields can trigger sudden releases of energy, particularly in magnetars. In some cases, these shifts produce bursts of X-rays and gamma rays observed by satellites. The connection between magnetic activity and crustal dynamics highlights how the outer layers, though thin relative to the star, govern many of its most observable features. The mechanical strength of the crust has been investigated using theoretical models of nuclear matter. Calculations suggest that the crust may be the strongest material known, able to withstand strains far greater than any earthly substance. This strength is necessary to support mountains, though these are tiny by human standards. A mountain on a neutron star might rise only a few centimeters before being crushed by gravity, but even such slight irregularities could produce detectable gravitational waves as the star spins. Advanced detectors may one day confirm the presence of such deformations, providing a new way to probe the crust properties. Beyond mechanical and thermal roles, the crust also plays a part in rotational behavior. As the star spins, the crust couples to the superfluid interior through a network of vortices, tiny whirlpools of quantum motion. Over time, the interaction between the crust and superfluid can lead to sudden changes in spin rate known as glitches. These events, observed in many pulsars, are thought to involve shifts in the crust that redistribute angular momentum. In this sense, the crust is a mediator between the deep interior and the observable rotation of the star. Observationally, the surface of the crust is visible in X-rays, especially in young neutron stars that are still hot. Space telescopes detect thermal emission from the surface, allowing astronomers to measure surface temperatures and estimate cooling rates. By modeling how this radiation emerges from the star's curved spacetime, scientists can also constrain its radius. Missions such as NASA's Neutron Star Interior Composition Explorer or NISA observe X-ray pulses from hotspots on the surface, mapping how light bends around the star. This data provides information about the star's mass and radius, which in turn constrains the physics of the crust and core. The crust therefore stands as more than a boundary. It is a laboratory for dense matter physics. It combines aspects of solid-state physics, nuclear theory, and astrophysics in a setting that cannot be reproduced on Earth. Its crystalline structure, nuclear pasta phases, and ability to support immense stress are features that expand our understanding of how matter behaves. By studying the crust through both theoretical models and observations of neutron stars, scientists continue to refine their picture of these extreme environments. The surface and crust of a neutron star also offer a natural stage where the consequences of extreme density gravity and quantum mechanics become directly observable. Each burst of radiation, each measured glitch, and each cooling curve carries within it information about this region. Though only a thin shell in comparison to the entire star, the crust defines how the interior reveals itself to the universe. In this way, the crust is both a shield and a messenger, enclosing the mysteries of the core while shaping the signals we detect across space. Beneath the crust of a neutron star lies the deep interior where the most extreme forms of matter in nature may reside. This region often divided into the outer core, and the inner core remains largely hidden from direct observation, yet it is central to the scientific questions about what neutron stars truly are. In the outer core, densities reach values similar to the interior of an atomic nucleus. Here, the matter is composed mostly of neutrons with a small fraction of protons and electrons. The presence of these charged particles is necessary to maintain electrical neutrality, and they allow currents to form that can sustain magnetic fields. The neutrons in this dense fluid are thought to behave as a superfluid, meaning they flow without viscosity. The protons being charged may form a superconducting fluid that carries electrical current without resistance. These properties are inferred from theory and are supported indirectly by observations of neutron star rotation glitches and cooling behavior. Superfluidity and superconductivity at nuclear densities represent conditions that cannot be recreated in laboratories on Earth. In terrestrial experiments, superfluid helium and superconducting metals exhibit some of these behaviors, but at densities far lower than those inside neutron stars. The interior of a neutron star therefore extends quantum mechanical phenomena into an unfamiliar regime. In this regime, vortices of superfluid neutrons align with the star's rotation, forming a lattice of quantized circulation. The movement and interaction of these vortices are thought to play a role in the sudden spin-up events known as glitches. Similarly, superconducting protons allow the magnetic field to be confined in quantized flux tubes, and the interaction between these tubes and neutron vortices may couple the magnetic field to the rotation. Deeper into the star at even higher densities, the structure of matter becomes more uncertain. The central density of some neutron stars may be several times nuclear density, raising the possibility of exotic faces of matter. One possibility is the appearance of hyperons, which are particles containing strange quarks. Another is the condensation of mesons, such as kaons or pions forming collective states. The most speculative possibility is that the inner core contains deconfined quark matter, in which protons and neutrons dissolve into a fluid of up, down, and possibly strange quarks. Such matter would be a new state of nuclear material predicted by some theories of quantum chromodynamics. The question of whether such exotic phases exist is tied to the so-called equation of state, which describes how pressure relates to density inside the star. Different theoretical models of dense matter predict different equations of state, leading to different mass-radius relations for neutron stars. Observations of the heaviest pulsars with masses about 2 times that of the Sun rule out some equations of state that are too soft to support such heavy stars. Measurements of neutron star radii using X-ray data from instruments like NISA provide further constraints. Gravitational wave detections from neutron star mergers also limit how deformable the stars can be under tidal forces, placing bounds on the stiffness of matter inside. Together, these observations are gradually narrowing the range of acceptable models, though uncertainty remains. Cooling behavior offers another indirect probe of the core. The rate at which a neutron star loses heat depends strongly on what particles can exist and how they interact. If exotic particles such as hyperons are present, they may allow rapid neutrino emission, cooling the star faster than expected. Observations of surface temperatures in young neutron stars compared with theoretical cooling curves help test these possibilities. For example, the cooling of the neutron star in the Cassiopeia, a supernova remnant, has been interpreted as possible evidence for the onset of neutron superfluidity in the core. While the interpretation remains debated, such data highlight the potential of thermal measurements to reveal interior physics. Glitches provide yet another window into the interior. These sudden increases in spin rate are thought to involve the transfer of angular momentum from the superfluid interior to the crust. The behavior of the vortices within the superfluid is central to this process. When pinned to the crust, the vortices can store angular momentum. If they suddenly unpin, they release it to the crust, causing the star to spin up slightly. The frequency and magnitude of glitches vary from one pulsar to another, suggesting differences in interior structure. These variations may reflect the thickness of the crust, the properties of the superfluid, and the presence of magnetic stresses. The deep interior also determines the ultimate fate of neutron stars under accretion. In binary systems where matter is transferred from a companion star, the neutron star can gain mass. If enough matter accumulates, the core may exceed the maximum mass supportable by the equation of state, leading to collapse into a black hole. Observationally, this transition has not been seen directly, but theoretical models predict that it should occur in some systems. The unknown maximum mass of neutron stars is therefore one of the most important questions in astrophysics, bridging stellar evolution, and fundamental nuclear physics. Laboratory experiments in nuclear physics inform these studies by measuring properties of dense matter under terrestrial conditions. Heavy ion collisions can create nuclear matter at densities near or slightly above nuclear saturation, though not at the low temperatures found in neutron stars. These experiments provide constraints on nuclear interactions that are then used in neutron star models. Still, the gap between laboratory densities and those in neutron star cores is large, leaving significant room for theoretical exploration. In this way, neutron stars act as natural laboratories that extend beyond the reach of human experiments. From a reflective perspective, the deep interior of a neutron star is a frontier where physics remains incomplete. The layers above can be described with more confidence, but the central core is accessible only through indirect clues. Each observation of a neutron star's mass radius cooling curve or glitch contributes a piece to the puzzle, yet the full picture is not yet known. Whether the core contains hyperons, meson condensates, or quark matter remains an open question. The challenge is that these states are predicted by quantum chromodynamics, a theory that is well established, but difficult to apply at high density and low temperature. Progress will depend on both improved astronomical observations and advances in nuclear theory. Thus, the deep interior of neutron stars stands as one of the most significant unknowns in modern astrophysics. It links the fate of massive stars with the behavior of fundamental particles under extreme conditions. By studying these interiors, scientists hope not only to understand neutron stars themselves, but also to expand knowledge of the strong nuclear force, one of the basic forces of nature. Each new observation brings the possibility of narrowing the uncertainties, yet the mystery remains. The crust may reveal itself in bursts and glitches, but the core holds secrets that only careful study of mass radius and gravitational waves can unlock. In this sense, the interior of neutron stars is not just a feature of astrophysics, but a key to understanding matter itself. Rotation is one of the most striking characteristics of neutron stars, and it follows directly from the conservation of angular momentum during stellar collapse. A massive star's core before collapse may rotate slowly, perhaps once every several days. When that core shrinks from thousands of kilometers in radius to only about 20 kilometers, its spin must increase dramatically, just as an ice skater spins faster when drawing in their arms. The result is a neutron star that can rotate multiple times per second, with some known to spin hundreds of times per second. These rapid rotations are not temporary bursts of motion, but can remain stable for millions or even billions of years, making neutron stars among the most precise rotators in nature. The stability of this rotation arises from the star's compactness and rigidity. Because a neutron star is small and incredibly dense, external torques that might slow it are weak compared to its moment of inertia. As a result, its spin decreases only slowly over time due to the emission of electromagnetic radiation and particle winds. For many neutron stars, the slowdown is measurable, but gentle, on the order of a fraction of a second over thousands of years. This makes pulsars, the rotating neutron stars that beam radiation toward Earth, excellent cosmic clocks. Their pulses can be timed with precision, comparable to atomic standards, allowing astronomers to detect tiny irregularities in rotation or influences from orbiting companions. The measured spin periods of neutron stars range widely. The slowest known rotate once every several seconds, while the fastest spin more than 700 times per second. Such extreme speeds are near the limit of what the material can withstand before centrifugal forces would overcome gravity. The existence of millisecond pulsars indicates that the neutron star material is strong enough to resist breaking apart under this strain. These rapid rotators are often found in binary systems where they have been spun up over time by accreting matter from a companion star. This process, sometimes called recycling, transfers angular momentum to the neutron star, reducing its spin period to just a few milliseconds. Rotation is not perfectly steady, however. Small irregularities occur in the form of glitches, sudden jumps in spin rate, or in slow variations called timing noise. Glitches are thought to be caused by the interaction between the solid crust and the superfluid interior. The vortices of the superfluid store angular momentum and can remain pinned to the crust until they suddenly unpin, releasing their stored momentum and causing the crust to speed up slightly. This manifests as a measurable increase in the rotation frequency. Timing noise, on the other hand, is less understood and may be related to complex magnetospheric processes or interior dynamics. Both phenomena remind scientists that the interior of the neutron star plays an active role in maintaining or disturbing rotational stability. The relationship between rotation and emission is also important. The beamed radiation observed from pulsars is tied to the star's magnetic field, which is anchored in the interior but tilted relative to the spin axis. As the star rotates, the beam sweeps across space. If Earth lies in the path of the beam, observers detect regular pulses at the spin frequency. These pulses provide a direct measure of the rotation period and its changes over time. In many cases, the stability of these pulses allows pulsars to serve as tools for studying other phenomena. For example, by timing the arrival of pulses over years, astronomers can detect the influence of orbiting planets, companions, or even the passage of gravitational waves stretching and compressing space-time between the pulsar and Earth. Rotation also affects how the star loses energy. The electromagnetic field of a rotating neutron star carries away energy, leading to a gradual slowdown. This spin-down process is predictable and can be modelled mathematically. By measuring the current spin rate and its rate of decrease, astronomers can estimate the magnetic field strength of the star. The spin-down also provides an approximate age known as the characteristic age, which can be compared with the age of the associated supernova remnant when one is present. In many cases, the agreement between these independent estimates reinforces the understanding of neutron star evolution. In binary systems, rotation couples with orbital motion in complex ways. Accretion of matter not only spins up the neutron star but can also create bursts of X-rays, as in falling matter releases gravitational energy. Some of these accreting pulsars show pulses in X-rays rather than radio waves, with the rotation modulating the visibility of hotspots where matter strikes the surface. These X-ray pulsars provide another way to measure spin and study how accretion affects it. Over long time scales, the interplay between accretion-driven spin-up and radiation-driven spin-down can lead to equilibrium states where the neutron star maintains a steady, rapid rotation. Rotational stability is particularly important for the subset known as millisecond pulsars. Their extraordinary steadiness allows them to be used as galactic clocks. Networks of such pulsars form what is called a pulsar timing array, which astronomers use to search for the faint background of gravitational waves produced by supermassive black hole binaries across the universe. Any systematic shift in the timing of pulses across the network may indicate the influence of such waves. This application shows how the simple fact of rotational stability in neutron stars extends to the study of cosmological processes far beyond their immediate environment. Despite this, precision rotation is not unchanging forever. Over millions of years, even the most stable pulsars gradually slow, and some eventually cross a threshold where their beams no longer reach Earth, or where their emission ceases entirely. At that stage, they become invisible to our telescopes, though they continue spinning silently. Others may be revived through accretion in a binary system, regaining rapid spin and emitting as pulsars again. The cycle of slowing, revival, and slowing again demonstrates the interplay between intrinsic rotation and external influences over cosmic timescales. Rotation also offers a way to measure the internal structure of neutron stars. The maximum possible spin rate depends on the equation of state, since a stiffer star can withstand faster spin before breaking apart. The discovery of a pulsar spinning over 700 times per second provides constraints on how compressible neutron star matter can be. Searches continue for even faster rotators, as each new detection could push these limits further. At the same time, the absence of pulsars spinning beyond a certain rate may indicate an intrinsic limit set by gravitational radiation or internal instabilities. Theories suggest that rapidly rotating neutron stars may lose angular momentum through gravitational waves if their shape is not perfectly symmetric. Detection of such waves would provide direct evidence of these rotational instabilities. In summary, the rotation of neutron stars is not a minor detail but a defining property. It connects the physics of collapse to long-term observables. It serves as a probe of interior superfluidity and magnetic fields. It influences emission across the electromagnetic spectrum, and it provides tools for studying phenomena far beyond the stars themselves. Whether in the slow pulses of a young radio pulsar, the rapid flicker of a millisecond pulsar, or the irregular jumps of a glitch rotation, is the steady heartbeat of neutron stars linking their violent origins with their enduring role in astrophysics. The magnetic fields of neutron stars are among their most remarkable and extreme features, shaping much of what astronomers observe. When the core of a massive star collapses, magnetic field lines frozen into the plasma are compressed dramatically. Just as rotation speeds up when the radius shrinks, magnetic field strength intensifies as the field is confined to a smaller area. If the progenitor star had a typical magnetic field of a few hundred Gauss, compression during collapse can raise the field to trillions of Gauss on the surface of the neutron star. By comparison, Earth's magnetic field is less than 1 Gauss, and even the strongest magnets built in laboratories rarely exceed a few 100,000 Gauss. Thus, the field of a neutron star is beyond any terrestrial experience. The presence of such intense fields is inferred both from theory and from observations of pulsars and X-ray sources. As the star rotates, its magnetic field generates electric fields that accelerate charged particles in the magnetosphere, the region of space dominated by the star's magnetic influence. These particles radiate energy in the form of radio waves, X-rays, and gamma rays. The magnetic field also channels accreting matter in binary systems, funneling it toward the magnetic poles, where it strikes the surface and produces hotspots. These processes mean that the magnetic field is not a hidden property but a controlling force in nearly every observable phenomenon linked to neutron stars. Field strength varies widely among neutron stars. Ordinary pulsars typically have magnetic fields around 1 trillion Gauss. Some called millisecond pulsars, which have been spun up by accretion, show weaker fields of about 1 billion Gauss, likely reduced during their recycling process. At the extreme are magnetars with surface fields up to 1 quadrillion Gauss. These fields are strong enough to influence the quantum vacuum itself, polarizing empty space and altering the propagation of light. In such conditions, even the structure of atoms would be distorted as the field dominates over the usual electromagnetic forces binding electrons to nuclei. The geometry of the magnetic field is generally approximated as a dipole, like a simple bar magnet tilted relative to the rotation axis. However, detailed models suggest that higher-order multipole components may also be present, especially near the surface. These complex structures can influence how beams of radiation are formed and how hotspots appear. Observationally, the shape of X-ray pulses measured by instruments such as NICER allows astronomers to infer the geometry of the magnetic field and its alignment with the spin axis. This information helps refine models of how pulsar beams sweep across space. Magnetic fields also affect the long-term evolution of neutron stars. The energy lost through magnetic braking slows the star's rotation over time. This spin-down is a key observable, and the rate of slowdown provides an estimate of field strength. For instance, pulsars with rapid spin-down rates are inferred to have stronger fields, while those with more stable spins have weaker ones. This relationship allows astronomers to classify neutron stars and estimate their ages. Characteristic ages derived from spin-down often match the ages of associated supernova remnants, lending confidence to the models. The magnetic field is also implicated in sudden energetic events. In magnetars, the twisting and shifting of magnetic fields within the crust can release enormous bursts of energy. These bursts appear as sudden flares of X-rays and gamma rays, some of which outshine the rest of the galaxy for a fraction of a second. Such events demonstrate that the magnetic field stores energy on scales comparable to the total luminosity of stars. Even in ordinary pulsars, smaller events may reflect magnetic stresses rearranging field lines in the magnetosphere. These processes are similar in principle to solar flares, but vastly more powerful due to the field strength involved. The structure of the magnetosphere determines how radiation escapes and how particles are accelerated. Models describe regions called open and closed field lines, with the open lines allowing particles to stream outward into space. The boundary between these regions, called the light cylinder, lies at the distance where the co-rotating field would move at the speed of light. Beyond this point, field lines cannot remain closed, and particles are flung outward. The interaction between the magnetic field, the rotation, and the plasma populating the magnetosphere creates a dynamic environment that gives rise to the observed pulses. At the quantum level, fields of this magnitude reveal phenomena unseen elsewhere. In magnetostrength fields, photons can split into lower energy photons, a process forbidden under normal conditions, but allowed when the vacuum is polarized. Electrons in such fields are forced into discrete energy levels, changing how they interact with radiation. These effects are not merely theoretical, but may be observed in the spectra of magnetar bursts. By studying these extreme processes, astrophysicists test fundamental physics in a regime unattainable in laboratories. The evolution of the magnetic field itself remains a subject of active research. The field may decay over millions of years, especially in magnetars whose high fields appear to weaken faster than those of ordinary pulsars. The decay is influenced by electrical currents in the crust and core, which in turn depend on the properties of superfluid and superconducting matter. Observations of pulsars across a range of ages support this picture, with older millisecond pulsars showing weaker fields consistent with gradual decay. Understanding how fields evolve is important not only for neutron star astrophysics, but also for explaining the diversity of observed sources from young energetic pulsars to quiet old stars detectable only in radio. Magnetic fields also connect neutron stars to the broader environment. Pulsar wind nebulae such as the Crab Nebula are powered by rotational energy channeled through magnetic fields into streams of relativistic particles. These outflows create luminous nebulae observable across the spectrum, linking the internal dynamics of the star to large-scale structures in space. In binary systems, magnetic fields regulate accretion, shaping how matter flows and how X-ray emission varies. In magnetars, the coupling of magnetic fields to the crust can drive starquakes that send ripples through the magnetosphere, producing detectable bursts. Each of these phenomena highlights how the magnetic field extends the influence of the neutron star far beyond its surface. For scientists, the study of neutron star magnetic fields is not only about describing the stars themselves, but also about probing the limits of physics. These fields compress plasma, alter atomic structure, and even modify the properties of the vacuum. They control radiation-drive winds and trigger bursts that we can observe across the galaxy. By analyzing pulses, spectra, and flares, astronomers reconstruct the invisible architecture of magnetic fields that are otherwise inaccessible. This effort continues to refine the understanding of how nature operates under its most extreme conditions. One of the most distinctive observational features of neutron stars is the phenomenon of beaming, which gives rise to pulsars. The strong magnetic field of a neutron star is not usually aligned with its rotation axis. As the star spins, the magnetic poles sweep around like the beams of a lighthouse. Charged particles accelerated along magnetic field lines near the poles emit radiation primarily in the form of radio waves, but also sometimes in X-rays or gamma rays. Because the beams are narrow, and directional observers on Earth only detect radiation when the beam passes across their line of sight. This produces a regular sequence of pulses that repeat with remarkable stability, each corresponding to one rotation of the star. The discovery of these pulses in the late 1960s provided the first clear evidence for neutron stars and marked the beginning of pulsar astronomy. The geometry of the beam depends on the alignment between the magnetic and rotational axes, as well as the structure of the magnetosphere. If Earth lies within the sweep of the beam, the neutron star is seen as a pulsar. If not, the star remains invisible at those wavelengths even though it is active. This geometry explains why only a fraction of neutron stars are observed as pulsars, despite the expectation that many more exist. Estimates suggest that for every pulsar detected, several others remain unseen due to beam orientation. The pulsar population observed today is therefore a subset shaped by viewing angle as much as by intrinsic properties. Pulsars are divided into categories based on their emission. Some emit primarily in the radio band, producing sharp pulses detectable with ground-based telescopes. Others shine in higher energy bands with X-ray or gamma-ray emission revealed by satellites. In many cases, the emission arises from regions in the magnetosphere where electric fields accelerate particles to near light speed. These particles radiate through curvature radiation, synchrotron emission, or inverse Compton scattering, producing beams of various wavelengths. The exact mechanism differs among pulsars and remains a subject of research, but the overall picture is consistent rotation and magnetic fields combine to produce beams of radiation sweeping through space. The precision of pulsar timing has made them essential tools in astrophysics. Because each pulse corresponds to a rotation of the neutron star, astronomers can measure arrival times of pulses with extraordinary accuracy. Some pulsars maintain stability over decades with deviations of less than a microsecond. This makes them natural laboratories for testing physical laws. For instance, binary pulsars where the neutron star orbits a companion allow tests of general relativity. By tracking the timing of pulses, astronomers can measure orbital decay due to gravitational wave emission, a phenomenon first confirmed in the famous Hulse-Taylor pulsar system. More recently, networks of millisecond pulsars are being used as galactic-scale gravitational wave observatory, searching for the subtle imprint of waves from supermassive black hole binaries. Pulsar emission also provides information about the environment of the neutron star. As radio pulses travel through the interstellar medium, they are dispersed by free electrons. The amount of dispersion depends on the density of electrons along the path, providing a measure of distance and mapping the structure of the galaxy. This property has made pulsars valuable probes of galactic plasma. Similarly, scattering and absorption effects modify pulses, revealing properties of intervening material. Thus, each pulsar acts not only as a clock, but also as a probe of the cosmic medium between stars. Not all pulsars are steady. Some switch between emission states turning on and off over timescales of seconds, minutes, or years. These mode changes suggest that the magnetosphere can reorganize itself, altering how particles are accelerated and how beams form. Others show drifting subpulses or changes in pulse shape, again pointing to complex plasma dynamics near the star. Some pulsars even disappear, completely entering long periods of radio silence before reappearing. These behaviors highlight the dynamic nature of the magnetosphere and the sensitivity of beaming to small changes in conditions. High-energy pulsars observed by gamma-ray telescopes reveal further insights. Their beams tend to be broader than those in radio, suggesting emission from outer regions of the magnetosphere. The light curves of these pulsars often show double peaks interpreted as emission from both magnetic poles or from extended arcs of field lines. By modelling the pulse shapes, astronomers reconstruct the geometry of the beams and test theories of particle acceleration. Each new detection refines the picture of how neutron star magnetospheres channel and emit energy. The role of beaming in neutron star studies cannot be overstated. It transforms rotation into observable pulses, allowing measurement of spin down and timing irregularities. It connects magnetic fields to emission, linking interior properties to external radiation. It enables astrophysical tests of gravity, plasma physics, and galactic structure. Without beaming, neutron stars would be far more difficult to detect and study, but with it they stand out as some of the most useful objects in the sky. At the same time, beaming introduces selection effects that must be carefully considered. Because we only observe pulsars whose beams cross our line of sight, the true population of neutron stars is larger than what surveys reveal. Correcting for this bias requires statistical models of beam width and orientation. Such models suggest that there may be hundreds of millions of neutron stars in the Milky Way, though only a few thousand have been detected as pulsars. Understanding beaming is therefore essential not just for interpreting individual objects, but for estimating the total neutron star population. From a broader perspective, the beaming of neutron stars illustrates how extreme physics manifests in accessible ways. The combination of rapid rotation, immense magnetic fields, and dense matter produces narrow beams that sweep across the cosmos with clock-like regularity. For scientists, these beams are both signals and tools, offering insight into the hidden interiors of neutron stars and the space through which their pulses travel. Each flash of a pulsar is a reminder that even in the quiet expanse of the galaxy, compact remnants of massive stars continue to mark time with unwavering precision. Among the many signals neutron stars provide, one of the most revealing comes from sudden changes in their rotation known as glitches. For most pulsars, the spin rate decreases gradually over time as energy is radiated away through electromagnetic waves and particle outflows. This slowdown is smooth and predictable to high precision. Yet in certain stars, astronomers observe abrupt increases in spin frequency, often amounting to a tiny fraction of a percent, followed by a slow relaxation toward the original trend. These events, called glitches, are thought to reflect processes deep inside the star, where superfluid neutrons and the solid crust interact in complex ways. The crust of a neutron star is solid and capable of storing stress as the star slows. Beneath it, the interior is expected to contain superfluid neutrons, which rotate by forming an array of quantized vortices. These vortices can pin to the lattice of nuclei in the crust, preventing them from moving outward as the star loses angular momentum. Over time, a mismatch builds between the slower spinning crust and the faster spinning superfluid. When the pinning force is overcome, vortices suddenly unpin and move outward, transferring angular momentum to the crust. This results in a rapid spin-up observed as a glitch. The crust then adjusts to the new state, and the slowdown resumes at its usual pace. Glitches vary in size and frequency. Some pulsars glitch frequently with small changes, while others experience rare but large jumps. The Vela pulsar, a relatively young and energetic neutron star, is famous for producing large glitches every few years. Monitoring this pulsar has provided much of the foundational data for glitch studies. The pattern of glitches suggests that the interaction between the superfluid and the crust is not uniform but depends on the properties of each star. Factors such as crust thickness, magnetic field strength, and temperature likely influence how stresses build and release. In addition to glitches, neutron stars sometimes show smaller irregularities known as timing noise. This phenomenon appears as a wandering of pulse arrival, times that does not follow a clear pattern. Timing noise is less well understood than glitches, but it may result from fluctuations in the magnetosphere, changes in current systems around the star, or slow rearrangements of the interior. Both glitches and timing noise remind scientists that neutron stars, though stable in many ways, remain dynamic systems influenced by forces deep within. Another class of events linked to the crust are starquakes. As the magnetic field evolves or as stresses accumulate from rotational slowdown, the rigid crust can fracture suddenly. This releases energy both mechanically and electromagnetically. In magnetars, starquakes are thought to trigger bursts of X-rays and gamma rays. The fracture disturbs the magnetic field lines anchored in the crust, sending waves into the magnetosphere that accelerate particles and produce intense radiation. These bursts can outshine the entire galaxy for a brief moment. The association between bursts and crustal activity highlights the importance of the solid outer shell in controlling observable phenomena. The study of glitches and star quakes provides a unique way to probe the physics of dense matter. Since the interior cannot be seen directly, these events act as indirect signals of what occurs beneath the surface. By measuring the size, frequency, and recovery of glitches, astronomers infer properties of the superfluid and its coupling to the crust. For example, the relaxation after a glitch may reflect the movement of superfluid vortices adjusting to the new configuration. The timescales of this recovery provide estimates of viscosity and interaction strengths in the dense interior. Observations of glitches are made possible by the extraordinary timing precision of pulsars. Even a change of 1 part in a million in rotation rate can be detected by tracking pulse arrival times over months and years. Radio observatories around the world contribute to these measurements, maintaining long-term monitoring of known pulsars. When a glitch occurs, astronomers record the sudden shift and adjust timing models accordingly. Over decades of study, hundreds of glitches have been catalogued, providing a statistical view of their distribution and properties. One notable result is that glitches are more common in younger pulsars with stronger magnetic fields. Older millisecond pulsars, which have been recycled through accretion, rarely show glitches, perhaps because their interiors are cooler and their superfluid dynamics differ. This distinction underscores how the evolutionary stage of a neutron star affects its behavior. Young stars are dynamic and prone to irregularities, while older stars are more stable and predictable. The link between glitches and neutron star interiors also extends to gravitational wave astronomy. A sudden rearrangement of mass within the star could in principle generate a brief gravitational wave signal. Current detectors are not yet sensitive enough to capture such events, but future instruments may search for them. If detected gravitational waves from glitches or starquakes would provide direct information about the distribution of matter inside neutron stars, complementing the electromagnetic observations already in hand. Glitches and starquakes also help distinguish neutron stars from other compact objects. Black holes, for example, cannot produce such events because they lack a solid surface and crust. The presence of glitches is therefore a strong indicator of the unique structure of neutron stars. Each event serves as a reminder that these stars are not inert remnants, but active systems shaped by both their outer layers and their hidden cores. The study of these sudden changes continues to evolve as new data accumulate. With more sensitive radio arrays and X-ray telescopes, astronomers are able to monitor larger numbers of pulsars and detect smaller events. Combined with advances in theoretical modeling of superfluid dynamics and crustal mechanics, this growing dataset is refining the picture of how neutron stars behave. While many details remain uncertain, the broad conclusion is clear. Glitches and starquakes are surface manifestations of deep, physical processes, offering rare glimpses into conditions that cannot be recreated on Earth. In this way, neutron star irregularities are more than anomalies in timing data. They are key phenomena that bridge observable signals and interior physics. Each sudden spin-up or burst of radiation is a piece of evidence that adds to the broader understanding of how matter behaves under extreme density gravity and magnetism. By continuing to monitor these events, astronomers slowly assemble a clearer view of the complex layered structure hidden within these compact stars. Among the various types of neutron stars, magnetars stand out because of their extraordinary magnetic fields and the dramatic bursts of energy they produce. While ordinary pulsars typically have surface magnetic fields of around 1 trillion Gauss magnetars, possess fields hundreds to 1,000 times stronger, reaching up to 1 quadrillion Gauss. At such field strength, the physics of matter itself is altered. Electrons are forced into their lowest energy states, atoms are stretched along magnetic lines, and the vacuum of space behaves differently, becoming polarized in ways that change how light propagates. Magnetaires are therefore not only fascinating objects in their own right, but also natural laboratories for testing fundamental physics under extreme conditions. The existence of magnetars was proposed to explain certain X-ray and gamma-ray sources that could not be accounted for by ordinary pulsars. These objects, called soft gamma repeaters and anomalous X-ray pulsars, emit sporadic bursts of high-energy radiation, as well as persistent X-ray emission stronger than what rotation alone could power. In the mid-1990s, the magnetar model was developed to account for these phenomena. According to this model, the decay and rearrangement of ultra-strong magnetic fields provide the energy for the bursts and persistent emission. Subsequent observations have supported this picture, and today magnetars are recognized as a distinct class of neutron stars. The bursts from magnetars vary in intensity. Some are small, lasting less than a second, and releasing as much energy as the sun emits in a year. Others are giant flares, rare events that release 100,000 times more energy in a fraction of a second. The most famous giant flare was detected in 2004 from a magnetar in our galaxy. It briefly saturated detectors and was visible even after bouncing off the moon's surface. Such flares demonstrate the immense energy stored in magnetic fields and how quickly it can be released when the crust shifts or when magnetic lines reconnect. The mechanism of magnetar activity is thought to involve the interaction between the magnetic field and the crust. As the magnetic field evolves and decays, it stresses the crust, which can fracture in starquakes. These fractures disturb the magnetic field lines anchored in the crust, causing them to twist and reconnect in the magnetosphere. The sudden reconfiguration accelerates particles and produces intense radiation. This process is analogous to solar flares but occurs at much higher field strengths, producing radiation in the X-ray and gamma-ray ranges rather than visible light. The link between crustal shifts and bursts is supported by observations of changes in rotation, following some magnetar flares indicating that the star itself has been physically disturbed. In addition to bursts, magnetars emit persistent X-rays that exceed what can be explained by spin-down energy alone. This emission is thought to be powered by the decay of magnetic fields inside the star, which release heat that diffuses outward. The field decay may proceed through processes such as ambipolar diffusion in the core and Hall drift in the crust. The exact details remain subjects of research, but the basic picture is that the magnetic field, rather than rotation, is the dominant energy source in magnetars. This distinguishes them from ordinary pulsars whose emission is powered mainly by rotational energy. Magnetars also exhibit unusual timing behavior. Some show large glitches while others have episodes of rapid spin-down linked to bursts of activity. These irregularities highlight the complex interaction between rotation magnetic fields and the crust. In some cases, the timing noise is so large that it obscures the underlying slowdown trend. Such variability further distinguishes magnetars from the more stable millisecond pulsars used as cosmic clocks. A topic of ongoing debate is the connection between magnetars and fast radio bursts, mysterious millisecond flashes of radio waves detected from cosmological distances. In 2020, a magnetar in our galaxy was observed to produce a radio burst similar to fast radio bursts, though much less powerful. This observation established that magnetars can produce such events at least locally. Whether all fast radio bursts arise from magnetars remains uncertain, as some appear to repeat and others do not, and their energies often exceed what has been seen from known magnetars. The magnetar hypothesis remains one of the leading explanations, but other possibilities such as interactions in binary systems or young pulsars are still considered. The study of magnetars requires observations across the electromagnetic spectrum. X-ray telescopes detect their persistent emission and bursts, while gamma-ray instruments capture the most energetic flares. Radio telescopes search for associated bursts. Optical and infrared observations sometimes reveal faint counterparts, though these are rare given the distances and obscuration by dust. Each wavelength provides a different perspective on the processes occurring in and around magnetars. Coordinated observations across multiple bands are particularly valuable, as they can capture both the immediate burst and the longer-term aftermath. Despite their rarity, only a few dozen magnetars are known in the galaxy. They have an outsized influence on astrophysics. Their flares can affect the Earth's ionosphere, demonstrating their power even across thousands of light years. Their bursts provide laboratories for studying quantum electrodynamics under extreme fields. Their possible connection to fast radio bursts links them to cosmological phenomena visible across billions of light years. By studying magnetars, scientists explore questions that reach from the scale of atomic physics to the scale of galaxies. Uncertainties remain. The detailed structure of magnetar magnetic fields, the precise mechanisms of energy release, and the connection to other types of neutron stars are all active areas of research. Some theories suggest that all neutron stars may be born with strong fields, and that only some retain or reveal them as magnetars. Others propose that specific birth conditions such as rapid rotation or dynamo action in the early star are required. Observations of young supernova remnants associated with magnetars may help distinguish these scenarios. Magnetars thus embody the extremes of neutron star behavior. Their magnetic fields reach the highest known strengths in the universe. Their bursts are among the most energetic events short of supernovae and mergers, and their physics challenges the boundaries of theory. They remind scientists that the compact remnants of stars are not passive end states, but dynamic systems where fundamental forces interact in extraordinary ways. Each burst, each flare, and each irregular pulse adds to the growing picture of how magnetism, rotation, and matter intertwine under the most extreme conditions nature provides. In many neutron star systems, the compact remnant does not evolve in isolation, but instead orbits with a stellar companion. When the companion is close enough and evolves in such a way that its outer layers expand, matter can flow from it toward the neutron star. This process is called accretion, and it provides one of the most powerful ways for neutron stars to reveal their presence. As gas spirals inward under gravity, it forms an accretion disk around the neutron star. Friction and turbulence within the disk heat the matter to millions of degrees, causing it to radiate strongly in X-rays. At the inner edge of the disk, the neutron star's intense magnetic field funnels material onto its magnetic poles, creating hotspots that radiate as the star rotates. The result is an X-ray pulsar with pulses modulated by the spin period of the neutron star. The luminosity generated by accretion is immense. Because the neutron star is so compact, matter falling onto its surface releases far more energy than it would falling onto an ordinary star. A gram of gas impacting the surface produces as much energy as the detonation of a large bomb. This is why accreting neutron stars can outshine entire galaxies in X-rays when observed from Earth, despite being only a few tens of kilometers across. The efficiency of this process makes neutron stars key targets for X-ray observatories in space, such as Chandra, XMM Newton, and NuSTAR. Accretion does not always proceed steadily. In many systems, gas accumulates on the neutron star's surface until conditions allow nuclear fusion to ignite explosively. These events, known as thermonuclear X-ray bursts, last for seconds to minutes and release energy comparable to a full day's worth of solar output. They provide a direct probe of conditions on the surface, including the composition of the accreted material and the properties of the crust beneath. Observations of burst-like curves and spectra allow astronomers to study how matter behaves when compressed under such intense gravity. In some cases, accretion drives the neutron star to spin faster. As matter transfers angular momentum, the rotation period shortens, eventually producing millisecond pulsars. This recycling process explains how old neutron stars, which would otherwise have slowed down, can be spun up again to extremely rapid rotation. Recycled pulsars often retain weaker magnetic fields, possibly due to the long accretion process altering their field structure. These millisecond pulsars are among the most stable rotators known and serve as precision tools for astrophysics. Their existence demonstrates how binary interactions can rejuvenate neutron stars and extend their observational lifetimes. Accretion also produces variability on longer timescales. Some systems show regular outbursts lasting weeks or months, during which the accretion rate surges and X-ray emission increases dramatically. These transient X-ray binaries are thought to result from instabilities in the accretion disk. When matter builds up in the outer disk, it eventually becomes hot enough to ionize hydrogen, altering the disk's viscosity and triggering an inward flow. Once the stored material is drained, the system returns to quiescence until the cycle repeats. Such behavior links neutron star astrophysics with broader studies of accretion in other contexts, such as black holes and white dwarfs. Magnetic fields play a central role in shaping how accretion proceeds. In strongly magnetized neutron stars, the inner edge of the accretion disk can be truncated by the field, and matter is channeled along magnetic field lines. This can create quasi-periodic oscillations in the X-ray light curve, which provide information about the disk's inner radius and the magnetic field strength. In weaker field systems, the disk may extend closer to the surface, producing different observational signatures. By studying these variations, astronomers infer details of both magnetic geometry and accretion physics. Accretion can also trigger more exotic phenomena. In rare cases, if the accretion rate is extremely high, the pressure of radiation can nearly halt in full, creating a balance where matter piles up near the neutron star. Such sources are called ultraluminous X-ray pulsars, and they appear brighter than would normally be allowed by the Eddington limit, the theoretical maximum for steady accretion. The discovery of these objects has challenged standard models and suggested that strong magnetic fields or beaming effects may allow higher luminosities. These findings show that even well-established principles can be tested and refined by observations of accreting neutron stars. Another form of outburst arises from unstable nuclear burning on the surface. In so-called superbursts, carbon ignition deep in the crust leads to eruptions lasting hours and releasing 1,000 times more energy than ordinary X-ray bursts. These rare events probe conditions much deeper in the crust, providing clues about the long-term accumulation of accreted material and the thermal structure of the star. By comparing the occurrence of superbursts with theoretical models, researchers learn about nuclear reactions at densities far beyond terrestrial experiments. Binary accreting systems are also sources of gravitational waves. Asymmetric accretion can create mountains on the surface, albeit tiny ones only centimeters high. Yet because the star spins rapidly, these deformations can emit continuous gravitational waves. Such signals have not yet been detected, but searchers continue with instruments like LIGO and Virgo. A confirmed detection would open a new window into the interaction between accretion crustal strength and gravitational radiation. Accreting neutron stars also evolve over time. Long episodes of mass transfer can significantly increase their mass, pushing them closer to the maximum mass allowed by the equation of state. If the mass grows too high, collapse to a black hole may occur. Observationally, this end state has not been seen directly, but theoretical models suggest it must happen in some fraction of systems. Thus, accretion not only reveals the properties of neutron stars, but also shapes their long-term fate. For astronomers, accreting neutron stars are invaluable because they combine extreme physics with observable variability. Their bursts, oscillations, and persistent emission provide data that constrain models of dense matter, nuclear burning magnetic fields, and binary evolution. Each flare of X-rays is a piece of evidence that connects theoretical predictions to real behavior. By monitoring these systems over years and decades, researchers piece together the complex story of how neutron stars interact with their companions and with the universe at large. In this way, accretion transforms neutron stars from silent remnants into some of the brightest beacons in the sky. Through the steady fall of matter, they reveal secrets of nuclear reactions, magnetism, and relativistic gravity. The interplay of mass transfer radiation and rotation demonstrates that even after their violent birth, neutron stars continue to evolve dynamically, shaped by their environments and by the laws of physics acting at the highest energies. When accretion has spun a neutron star up to very high rotational speeds, the result is a millisecond pulsar. These objects rotate hundreds of times per second, completing a full turn in less time than a blink of an eye. The idea that old neutron stars could be recycled by accretion was first suggested to explain why some pulsars were spinning much faster than expected for their age. Over time, as a companion star donates, mass angular momentum is transferred to the neutron star, gradually increasing its spin rate. This process can continue for millions of years, eventually producing a neutron star that spins in only a few milliseconds. The evidence for this recycling scenario comes from observations of binary systems where accretion is ongoing. In some systems called low-mass X-ray binaries, the companion star is small, often a star similar to the Sun or even smaller. gas flows steadily onto the neutron star, creating an accretion disk that radiates strongly in X-rays. Embedded in the X-ray light are pulsations tied to the neutron star's spin, revealing that the accretion flow is transferring angular momentum. Over time, as mass builds up, the neutron star spins faster, and its magnetic field weakens, leaving behind a rapidly rotating but relatively faint pulsar once accretion ceases. Millisecond pulsars are among the most stable rotators in nature. Some are so steady that their pulses can be predicted years in advance with sub-microsecond precision. This stability makes them invaluable tools for testing physics. In binary systems, their timing has been used to measure general relativistic effects, such as Shapiro delay, gravitational redshift, and orbital decay. These measurements have confirmed Einstein's theory of gravity in regimes of strong fields. Millisecond pulsars are also used in pulsar timing arrays, where dozens of them are monitored together to search for long-wavelength gravitational waves passing through the galaxy. The principle is that gravitational waves will alter the distance between Earth and the pulsars in subtle ways, changing the timing of pulses in correlated patterns. This technique has already provided evidence for a background of gravitational waves likely produced by supermassive black hole binaries. The formation of millisecond pulsars also connects to the diversity of neutron star populations. Not all accreting neutron stars become millisecond pulsars. The outcome depends on how long accretion continues and how much angular momentum is transferred. Some systems end when the companion star loses most of its mass, leaving behind a white dwarf orbiting the neutron star. These so-called recycled pulsars with white dwarf companions are common, and their properties are consistent with the recycling model. Other systems may disrupt entirely, leaving isolated millisecond pulsars that still carry the rapid spin from their past accretion history. In addition to their role as cosmic clocks, millisecond pulsars provide insights into dense matter physics. Because their rapid rotation pushes the limits of structural stability, the maximum observed spin rate constrains the equation of state of neutron star matter. If neutron stars were too soft, they could not withstand the centrifugal force at high spins. The fastest known pulsar rotates more than 700 times per second, setting a firm lower limit on how stiff the equation of state must be. Searches for even faster pulsars continue, since discovery of a star spinning at 1,000 times per second would place even stricter limits. Millisecond pulsars also interact with their companions in intriguing ways. Some are found in systems called Black Widow and Redback binaries, where the pulsar's radiation is powerful enough to strip material from a low-mass companion. These systems show eclipses in radio emission, as the companion's wind blocks the pulses, and they provide natural laboratories for studying the interaction between pulsar winds and stellar atmospheres. Over time, the companion may be ablated entirely, leaving an isolated millisecond pulsar. This process demonstrates how extreme environments can reshape stellar systems on long timescales. Observations of millisecond pulsars also provide unique probes of galactic structure. As radio pulses travel through interstellar plasma, they are dispersed and delayed. Measuring this dispersion across many pulsars maps the distribution of free electrons in the galaxy. Millisecond pulsars, with their precise timing, offer especially accurate measurements. This mapping helps refine models of the galactic medium, which in turn improves the accuracy of pulsar timing arrays and distance estimates. In globular clusters, which are dense collections of ancient stars, millisecond pulsars are found in large numbers. The high stellar densities make interactions and exchanges between stars more common, creating conditions favorable for the formation of recycled pulsars. Some clusters host dozens of millisecond pulsars, offering rich laboratories for studying stellar dynamics, binary evolution, and the end states of stars. Their abundance in these clusters contrasts with their relative rarity in the galactic field, showing how environment influences neutron star evolution. The connection between accretion and recycling has been observed directly in transitional systems, which switch between being X-ray binaries and millisecond pulsars. In these systems, accretion sometimes dominates producing X-rays, while at other times the pulsar mechanism reactivates and radio pulses are observed. The switching demonstrates in real time the evolutionary link between accreting neutron stars and recycled pulsars. Such transitional pulsars confirm that accretion can indeed rejuvenate neutron stars, providing a bridge between theory and observation. The scientific value of millisecond pulsars extends beyond neutron star astrophysics. Their extreme rotational stability makes them testbeds for gravitational physics, galactic astronomy, and even cosmology. By acting as precise timing sources scattered across the sky, they create a network that can detect tiny distortions in space-time caused by distant massive objects. This use of millisecond pulsars effectively turns the galaxy into a detector, showing how the physics of compact stars connects to the dynamics of the universe as a whole. For researchers, the appeal of millisecond pulsars lies in their dual role as both end states of stellar evolution and as tools for fundamental science. They are remnants of massive stars spun up by long periods of accretion, yet they serve as instruments for probing forces and particles across cosmic scales. Their beams mark time with astonishing steadiness, while their very existence pushes the limits of nuclear matter and gravity. The study of these recycled pulsars therefore combines astrophysics, particle physics, and general relativity in a single field of inquiry. Millisecond pulsars illustrate how neutron stars, though tiny, on astronomical scales can have an influence that reaches far beyond their immediate surroundings. From binary interactions that alter stellar lives to gravitational wave signals that trace the growth of black holes to constraints on the most fundamental forces of nature, these stars occupy a central role in modern astrophysics. Their rapid pulses continue to sweep across Earth, silent but regular, offering scientists both a challenge and an opportunity to decode the messages of the universe, written in the timing of stars compressed into city-sized spheres. When two neutron stars orbit one another in a binary system, their mutual gravity gradually pulls them closer together. This slow-in spiral is driven by the emission of gravitational waves, ripples in space-time predicted by Einstein's theory of general relativity. Each orbit loses a tiny amount of energy to gravitational waves, causing the separation to shrink over millions or billions of years. As the stars draw nearer, their orbital period shortens and eventually they spiral together in a cataclysmic merger. These events are rare on human timescales, but they occur frequently enough in the galaxy to be observed with modern instruments. The collision of two neutron stars is one of the most violent and revealing events in astrophysics, producing not only gravitational waves, but also electromagnetic signals across the spectrum and newly synthesized heavy elements. The physics of the inspiral is remarkably precise. By timing pulsars in binary systems, astronomers have confirmed the gradual loss of orbital energy exactly as predicted. The famous Hulse-Taylor binary pulsar provided the first indirect proof of gravitational waves by showing that the orbit shrank at the rate expected from Einstein's equations. Decades later, in 2017, the LIGO and Virgo observatories directly detected gravitational waves from a binary neutron star merger known as GW17087. This detection confirmed the theory beyond doubt and opened a new era of multi-messenger astronomy, where both gravitational and electromagnetic signals are combined to study the same event. As the neutron stars spiral together in the final seconds, tidal forces distort their shapes. These distortions imprint themselves on the gravitational wave signal, providing information about how compressible neutron star matter is. This in turn constrains the equation of state, the relation between pressure and density in ultra-dense matter. By analysing the waveform of G717, scientists were able to place new limits on how stiff or soft neutron star matter can be. This demonstrates how collisions not only mark the end of binary systems, but also probe the physics of matter at nuclear densities. When the two stars finally collide, the outcome depends on the combined mass. In some cases, the merger may produce a massive neutron star that survives temporarily before collapsing into a black hole. In others, the collapse to a black hole happens almost immediately. Regardless of the exact sequence, the violent dynamics eject material at high speeds into space. This ejected matter is rich in neutrons and provides the perfect environment for rapid neutron capture known as the R process. The R process builds heavy elements such as gold, platinum, and uranium, which cannot be formed in ordinary stellar fusion. Observations of GW7707 confirm this process by detecting the signature of a kilonova, a transient glow powered by the radioactive decay of freshly synthesized nuclei. The kilonova accompanying a merger is distinct from a supernova. It is dimmer in visible light but brighter in infrared as the heavy elements absorb and re-emit radiation. The kilonova observed in 2017 matched predictions of R-process nucleosynthesis, providing direct evidence that neutron star mergers are a primary source of the universe's heaviest elements. This discovery connected the physics of compact objects with the chemical history of galaxies, and even with the origin of precious metals on Earth. The merger process also produces short gamma-ray bursts, intense flashes of high-energy radiation, lasting less than 2 seconds. These bursts had long been suspected to come from compact binary mergers, but proof was lacking until GW170017, which was accompanied by a gamma-ray burst detected by the Fermi satellite. The combination of gravitational waves, gamma rays, and later X-rays, radio waves, and optical signals provided a comprehensive view of the event. This multi-messenger approach confirmed theoretical predictions and demonstrated the power of coordinated observations across different types of detectors. The study of binary neutron star mergers extends beyond a single event. Each detection provides unique data about stellar evolution, nuclear physics, and cosmology. For example, the time delay between the gravitational waves and the gamma-ray burst in GW170817 allowed scientists to test the speed of gravitational waves, confirming that they travel at the speed of light to extraordinary precision. The luminosity of the kilonova also provided a new method to measure cosmic distances, offering an independent way to constrain the expansion rate of the universe. Thus, mergers link the smallest scales of nuclear matter with the largest scales of cosmology. Future detections will refine these results. As gravitational wave observatories become more sensitive, dozens or hundreds of neutron star mergers may be observed building a statistical sample. This will improve estimates of the rate of such mergers in the universe and clarify how often they produce black holes or stable neutron star remnants. With more data, the uncertainties in the equation of state will shrink, and the role of mergers in producing heavy elements will be quantified more precisely. Already, models suggest that a significant fraction of gold and other R-process elements in the universe originates from these collisions. The dynamics of the merger itself are complex. As the stars come into contact, shocks heat matter to billions of degrees, producing neutrinos, and potentially magnetic fields strong enough to launch relativistic jets. These jets are believed to be the engines of short gamma-ray bursts. Numerical simulations on supercomputers attempt to model these processes, incorporating general relativity nuclear physics neutrino transport and magnetohydrodynamics. The agreement between these simulations and observations of GDUS 19817 supports their validity, though many details remain open. For instance, whether the remnant temporarily supported by rotation can survive long enough to power extended emission remains debated. Binary neutron star mergers also differ from neutron star black hole mergers, which have also been detected. In those cases, the neutron star may be swallowed whole, leaving little or no electromagnetic counterpart. The presence or absence of ejecta depends on the masses and spins of the objects involved. By comparing different types of mergers, astronomers hope to map out the variety of outcomes and the corresponding observational signatures. For scientists, the significance of neutron star mergers lies in their ability to unite many fields of study. They involve stellar evolution, since the binary must survive 2 supernovae to form. They involve nuclear physics, since the equation of state determines the gravitational wave signal. They involve nuclear synthesis, since R process elements are forged in the ejecta. They involve high-energy astrophysics, since gamma-ray bursts and jets emerge from the collision. And they involve cosmology, since gravitational waves provide a new way to measure distances. Each detection therefore acts as a nexus of information that extends across the entire landscape of physics and astronomy. In summary, binary neutron star mergers represent some of the most consequential events in the universe. They destroy stars, yet create heavy elements. They emit gravitational waves that test relativity and light that maps cosmic distances. They show how extreme matter behaves under crushing gravity, and how magnetic fields and shocks can launch jets at near light speed. For astronomers, each merger is both an end and a beginning. The end of 2 neutron stars' lives in orbit, and the beginning of a flood of data that reveals fundamental truths about the cosmos. The study of neutron stars relies on a wide range of observational tools, each tuned to detect different signals and reveal different aspects of their structure. At the foundation is radio astronomy, which has been central since the discovery of pulsars. Large ground-based radio telescopes track the regular pulses of radiation emitted as beams sweep past Earth. By recording the arrival times of these pulses with microsecond precision, astronomers construct rotation histories spanning decades. From these measurements, they determine spin periods, spin-down rates, and timing irregularities such as glitches. Arrays of radio dishes such as the Very Large Array in New Mexico and Meerkat in South Africa add sensitivity and resolution, enabling the discovery of faint pulsars in distant regions of the galaxy. Radio timing has become one of the most important methods for probing the stability of neutron stars and for detecting effects predicted by general relativity. X-ray observations provide another window, especially into the surfaces and inner regions of neutron stars. Because these stars are compact and hot, they emit strongly in the X-ray band, particularly in their youth, or when accreting matter from a companion. Satellites such as Chandra, XMM, Newton, and NICA aboard the International Space Station detect this radiation. NICA in particular measures X-ray pulses from hotspots on the surface. By modelling how light bends around the star in its strong gravity, astronomers estimate mass and radius simultaneously. These measurements constrain the equation of state of dense matter, offering rare insights into what lies within. Thermal emission observed in X-rays also reveals cooling rates, which in turn test theories of neutrino emission from the interior. In accreting systems, bursts of X-rays from unstable nuclear burning provide direct evidence of conditions on the surface and in the crust. Gamma-ray instruments extend observations to the highest energies. The Fermi Gamma Ray Space Telescope has detected hundreds of pulsars emitting in gamma rays, including some that are invisible in radio. These gamma-ray pulsars often show different beam geometries, suggesting that their emission arises from outer regions of the magnetosphere rather than near the surface. The high-energy light curves and spectra test models of particle acceleration and magnetic field structure, gamma-ray bursts from magnetars and from neutron star mergers are also detected by these instruments, linking compact stars to some of the most energetic events in the universe. Optical and infrared observations, while less common, sometimes detect counterparts to neutron stars. The Crab pulsar, for example, emits pulses visible even in optical light detectable with high-speed instruments. Infrared observations reveal cooling emission from magnetars and counterparts to X-ray binaries. Though faint, these detections provide additional constraints on temperature and environment. In rare cases, fast optical bursts have been associated with magnetar activity, showing that neutron stars can produce signals across the entire spectrum. Beyond electromagnetic observations, gravitational wave detectors have revolutionized the study of neutron stars. LIGO, Virgo, and Kagra measure distortions in spacetime produced by colliding neutron stars. The waveform of these signals encodes information about mass radius and tidal deformability. The detection of GW17-817 confirmed that binary neutron star mergers are powerful sources of gravitational waves and provided data on the equation of state. Future detections will build a catalogue of events, refining measurements, and potentially revealing new phenomena such as continuous gravitational waves from spinning neutron stars with asymmetries in their crusts. These detectors are continually improving, promising more frequent and precise detections in the coming years. Neutrino observatories provide yet another messenger. Though only detected once so far in connection with a supernova in 1987, neutrinos are expected to flood out of collapsing stars as they form neutron stars. Modern detectors such as Super Kamiokande and IceCube are ready to capture neutrino bursts from the next nearby supernova. Such a detection would offer direct insight into the core collapse process and the birth of a neutron star. Combined with gravitational waves and electromagnetic signals, neutrinos would complete the multi-messenger picture, allowing astrophysicists to reconstruct events in unprecedented detail. Each observational tool has strengths and limitations, but together they form a comprehensive approach. Radio pulses provide timing and precision. X-rays reveal surfaces and interiors. Gamma rays highlight magnetospheres. And bursts, gravitational waves, probe collisions, and neutrinos carry information from deep within. The multi-messenger detection of GW17-817 showed the power of this approach as telescopes across the world observed the aftermath of the merger from gamma-ray flashes to infrared kilonova emission to radio afterglows. This event demonstrated that only by combining all available signals can the full complexity of neutron stars be understood. Observations also extend beyond individual stars to populations. Surveys with large radio arrays discover new pulsars, expanding the census and allowing statistical studies of their properties. X-ray and gamma-ray missions catalogue sources across the galaxy, identifying classes of neutron stars such as magnetars and accreting binaries. Pulsar timing arrays link dozens of millisecond pulsars into networks that search for gravitational waves from distant black holes. These efforts show that neutron stars are not isolated curiosities, but part of a larger fabric of astrophysical processes. Advanced analysis techniques further extract information from data. In X-ray timing, pulse profile modeling compares observed light curves with predictions from general relativity, yielding constraints on radius and mass. In radio timing, tiny variations in arrival times reveal the presence of exoplanets orbiting pulsars as in the first exoplanet discovery around PSR B.1257/12. In gravitational wave data matched filtering compares observed waveforms with theoretical templates to identify signals buried in noise. Each method refines our understanding by linking observation to theory with increasing precision. The future promises even more powerful tools. The Square Kilometre Array under construction in South Africa and Australia will detect tens of thousands of new pulsars, including rare types, that may push the limits of known physics. The European Space Agency's Athena X-ray Observatory, planned for the next decade, will probe neutron star surfaces and accretion disks with unprecedented sensitivity. Upgrades to gravitational wave detectors will increase the volume of space surveyed, bringing many more merger detections. Proposed neutrino observatories will capture signals from supernovae across the galaxy. Together, these advances will transform the study of neutron stars from a field driven by rare discoveries into one of abundant data and detailed exploration. In reflecting on observational tools, it is clear that no single method can capture the full reality of neutron stars. Their compactness, density, magnetism, and dynamics manifest in different ways across the spectrum and across messengers. By weaving together these signals, astronomers build a coherent picture of objects that cannot be probed directly. Each telescope, each detector, and each observation adds a piece to the puzzle, narrowing uncertainties and uncovering new phenomena. Neutron stars thus exemplify the value of a multi-messenger, multi-wavelength approach in which diverse instruments collaborate to illuminate the most extreme physics in the cosmos. Despite decades of study, neutron stars still present open questions that drive ongoing research. One of the most fundamental uncertainties concerns the maximum mass a neutron star can support before collapsing into a black hole. Observations of pulsars with masses around 2 times that of the Sun show that the equation of state of dense matter must be stiff enough to hold up such heavy stars. Yet how much higher this limit extends is unclear. Some models allow up to 2.5 solar masses, while others suggest slightly lower thresholds. The true maximum mass depends on the behavior of matter at densities several times greater than that inside atomic nuclei, a regime inaccessible to experiments on Earth. Precise measurements of pulsar masses, especially in systems with white dwarf companions, continue to narrow the range, but a definitive answer has not yet emerged. The interior composition of neutron stars is another enduring puzzle. While the outer crust and core are understood in broad terms, the innermost core may host exotic phases of matter. These could include hyperons, meson condensates, or even deconfined quark matter, where protons and neutrons dissolve into their constituent quarks. Each possibility leads to different predictions for the equation of state, and thus for observable properties such as radius and cooling behavior. Current observations are not yet precise enough to distinguish among these options. Future measurements of radius from X-ray pulse modeling and of tidal deformability from gravitational waves may help determine which form of matter exists deep inside. Until then, the true nature of the inner core remains an open question at the frontier of nuclear physics. The origin of fast radio bursts is another area where neutron stars may hold the answer, but uncertainty persists. These brief, intense flashes of radio waves lasting only milliseconds have been detected from galaxies billions of light-years away. Some repeat while others are seen only once. Their energies are enormous and their precise origin is debated. Magnetars are strong candidates supported by the detection of a burst from a galactic magnetar in 2020. Yet whether all fast radio bursts arise from magnetars is not certain, as some appear too energetic or show patterns difficult to reconcile with known magnetar behavior. Other possibilities include young pulsars, interactions in binary systems, or processes near black holes. The connection between neutron stars and fast radio bursts is compelling but not fully resolved. Another uncertainty involves how neutron stars form and evolve across different environments. While core collapse supernovae are the primary channel, some neutron stars may arise from electron capture supernovae, where less massive progenitors collapse under the capture of electrons by nuclei. These events produce lighter neutron stars and may account for certain observed masses. The role of fallback accretion, where some ejected material falls back onto the remnant, also complicates the picture. Such processes influence the birth properties of neutron stars, including their magnetic fields and spin rates. Understanding these formation pathways requires both detailed modeling and more observations of young neutron stars in supernova remnants. The long-term evolution of magnetic fields is also debated. Do all neutron stars begin with magnetar-level fields that decay rapidly, or do only some acquire such extreme magnetism at birth? Observations suggest diversity, but the underlying physics is unclear. Field decay mechanisms involving processes in the crust and core remain challenging to model. These uncertainties affect not only magnetar studies, but also the understanding of pulsar populations as a whole, since magnetic field strength governs spin-down and emission properties. Gravitational wave astronomy has opened new possibilities but also new questions. The detection of G-BubB 70817 confirmed that binary neutron star mergers occur, but the variety of possible outcomes is still uncertain. How often does the remnant survive temporarily as a hypermassive neutron star before collapsing to a black hole? How much mass is ejected, and how does this depend on the equation of state? How significant are mergers as sources of heavy elements compared to supernovae? Each merger detected in the coming years will refine these estimates, but as of now the answers remain incomplete. The possibility of continuous gravitational waves from isolated neutron stars also remains open. If a spinning neutron star is not perfectly symmetric, even small mountains on its surface could emit steady gravitational radiation. Searches with LIGO and Virgo have placed upper limits on such signals, but have not yet detected them. Whether these waves exist at detectable levels depends on the strength of the crust, the presence of superfluid vortices, and the dynamics of magnetic fields. Future more sensitive detectors may resolve this question, adding another channel for probing the interior. Cooling behavior presents another unresolved issue. Some neutron stars cool faster than models predict, possibly due to enhanced neutrino emission from exotic processes in the core. Others remain hotter than expected, suggesting different internal compositions. The interpretation of these observations is complicated by uncertainties in surface composition, magnetic field geometry, and accretion history. Continued X-ray monitoring of cooling neutron stars combined with theoretical advances will be necessary to clarify these patterns. The diversity of neutron star populations also poses questions. Why do some become radio pulsars while others remain radio quiet? Why do certain stars evolve into magnetars while others do not? What governs the transition between accreting X-ray pulsars and recycled millisecond pulsars? The answers likely lie in initial conditions such as mass spin and magnetic field at birth, as well as environmental influences from binary companions. Yet the relative importance of each factor is still being worked out. From a broader perspective, neutron stars illustrate the limits of current knowledge. They are small enough to be influenced by quantum mechanics, dense enough to probe nuclear forces, massive enough to curve space-time strongly, and dynamic enough to produce signals across the spectrum and beyond. Each line of evidence radio pulses, X-ray spectra, gamma-ray bursts, gravitational waves, and neutrino detections provides a partial view. The challenge is to integrate these views into a coherent model that accounts for all observations while remaining consistent with fundamental physics. This synthesis is ongoing, with progress measured in incremental steps rather than sudden breakthroughs. Despite uncertainties, the scientific consensus is firm on key points. Neutron stars are formed in the collapse of massive stars. They are composed of matter at or above nuclear density. They exhibit extreme magnetic fields and rapid rotation, and they manifest as pulsars, magnetars, X-ray sources, and merger progenitors. Their study has already confirmed predictions of relativity, revealed new states of matter, and explained the origin of heavy elements. The open questions do not reflect ignorance, but the natural frontier of science, where theory and observation converge at the edge of the unknown. In contemplating what remains unknown, neutron stars highlight both the power and the limits of human inquiry. They show how much can be learned from careful observation of distant objects, and how much remains hidden until technology advances. Each unanswered question is not a barrier, but an opportunity, a reminder that the universe contains realms of physics still waiting to be explored. With each new telescope detector and simulation, the picture sharpens, but the full story of neutron stars is still unfolding, written in the pulses, flares, and waves that reach us across space.